a little bit. Yeah. Yeah. One student sent me a message, asked me to do a few more examples in class. Yeah. So I think it's a, reasonable request. So I will try my best to do more examples. Right? Yeah. So although, we need to cover a lot of materials, but I try my best to squeeze some time, to work on question. You ask me? Oh, yeah.
Yeah, so there's a question about the quiz that you're going to assign this weekend.
Yeah, this weekend. I haven't. I will.
You will?
I will.
What day is it assigning?
They usually weekend, early weekend, for example, Friday night, due next Sunday night, end of Sunday, Usually we follow this pattern, early weekend, then end of weekend, more than 1 week, All right, so I try to do examples, I try to, reserve some time devoted to examples. So I plan to do this way. All right. After the break time. So here, because I need to spend quite some time on examples, so I try to squeeze time as much as I can. All right. First, I do not check your attendance to squeeze some time. Second, the break time from 7 to 7:10. So I will start at 7:10. So break time, 10 minutes, exact 10 minutes. Second, after that, when I start at 7:10, I do examples. Okay, I call it a problem-solving session. So I call it little problem-solving session. All right, So I use the number 1, 2, 3, 4. Every class we have 1 20-minute little problem-solving session. How about that? Every class from 7:10 to 7:30. So we do 20-minute little problem-solving session. Today, number 1. Today, the first one. So then we use this way. Okay. I try to cover 2 problems every time. We do 2 problems, each problem session. Today 2. All right. So using this way, hopefully, can help you get better in problem solving. All right, so that's the change. Oh, someone joined, another student. I use this admit. So I start PowerPoint slides here, but I need to use that one to accept students. Because some technical problem. So let's start. We did B.1 last time. So today we start from B.2. A little slow. Just a minute. A little slow. I noticed a problem. Let me check it. Last time I noticed the lagging problem. So when I do handwriting, there is some significant lagging. So let me check it before I start. Because because that something. Let me see. OneDrive. OneDrive Oh, yeah. Another student joined us. Yeah, anyway, yeah. Yeah, the lagging. All right, yeah. Anyway, yeah. Let me just, ignore it. Yeah. In the break time, I will try another time. Yeah. All right, so let's start. Yeah. All right, yeah, yeah. The topic, existence theorem, here. So this topic, look at the title of our part B, existence and a uniqueness of solutions. So this is a theory part. Yeah. Most of our content, we do problem solving. We do computation. Yeah. But this theorem is very important. So I have to talk about existence and uniqueness problem. So this part, we do that. Yeah. Actually, in our first order linear ODEs, we have this problem. But I didn't do it. Yeah, I skip it. So here, when I talk about second order, I do together. Okay? So I do the first order first, after that, second order. So there, because the background is the same, so we can save some time. Yeah. Save some setup time. Yeah. All right, so let's look at the first order existence theorem for first order linear ODEs. Yeah. Because we may not know if the solution exists or not. So we need to have some theorem that guarantees the existence of the solution. Then we have confidence. Yeah. All right, so let's look at that theorem. Consider the initial value problem, first order, the general case. All right. Now, let's look at a simple example for existence. Here I want to give you two examples to see this question, existence. All right. The first one, absolute value of y prime plus absolute value of y equals 0, initial value. You can easily see this equation cannot have any solution. Because if it has a solution, each absolute value term must be 0. Then y must be a 0 function. Y equals 0. But if y equals 0, how can you get y of 0 equals 1? Contradiction. Yeah. So it's easy to see there is no solution, but we feel it's not a linear ODE, because when you put an absolute value sign, it's not a linear function anymore. Yeah. And we want to look at the linear case. Yeah, so it's not a linear example. Okay, yeah. All right. So let's look at another example here. Yeah. All right. This time, this is a linear first order ODE. Yeah, so no problem. Yeah. And initial value. Yeah. Now let's try to solve it. Yeah. Because it's very easy, separable. Yeah. So let's use the separable structure to solve it. Yeah. All right. Then we just do simple integration. Both sides, we get this expression. Yeah. C star. Yeah. So then we want to remove absolute value in our expression of the solution. But in order to remove the expression, we need to consider plus minus sign. Yeah. Here we want to cover all the solutions. So we have to consider the absolute value sign. Yeah. But here, how to make it simple here? Because this looks like not clean, right? Not neat. Yeah. We want something neat. Yeah. Yeah. Anyone have suggestion? Suggest how to make it as simple as possible? Yeah. All right. Positive, negative case. There is another thing here. When we write the general solution, we don't look at the initial condition. Okay, let's forget about initial condition. After we get a good general solution, then the last step, we plug in values to get an initial, get a particular solution. Yeah. So at this point, forget about the initial condition. Okay, can we make it simpler? We want a neat version. Yeah, this is, messy. We don't like this, messy form, neat form. Yeah, when you forget about the initial condition, can you see there is a zero solution? Y equals 0. Both sides 0. Both sides 0, right? It's a solution. Y equals 0 is a solution. That means we can include 0 also here, right? Because this expression cannot be 0, right? So we can add 0 to it. That expression cannot be 0. E function, how can E function be a 0? Right? You cannot. But now we add to it. How about that? We add 0 to E function. Any idea? Make it clean, neat version? Just C. How about that? C arbitrary constant. How about that? That constant could be positive, could be negative, could be 0. How about that? Is that neat? Yeah? All right? Yeah? So here, get experience. All right? After you do simplification at this point, now you can make a, good, neat, general solution. After we get general solution, then we plug in the initial values to find the C value. Last step. Yeah. In order to determine the C value, then we use the initial condition. All right? Yeah. So general solution, don't look at the initial condition because that would make some distraction. Okay? Yeah. So discourage you, yeah, because you worry something. Yeah. All right? But after you plug in the numbers y of 2, 2 minus 2, 0, it cannot be 0 times C, it cannot be 1. You cannot find a C that make your solution satisfy the initial condition. What's the conclusion? Yeah, no solution. The conclusion is this IVP, initial value problem, does not have any solution. Yeah, from this example, this is a legitimate linear first order ODE. That one is not. So people can argue, so it's not a linear first order ODE. So we don't want to look at that. But this one is a legitimate linear ODE, first order. Okay? Yeah? But it does not have any solution. That means we need to consider the existence, the title, existence of the solution. It's an important question. Yeah. All right. Now, can you observe anything special here? Why it does not have any solution? When you look at this equation, can you see something special that causes no solution problem? Observation. I emphasize the importance of observation. So here, can you see something that very special? Yeah. Let me write that equation to the standard form. Standard form. Because that's not a standard form. Okay? Standard form, y prime equals a certain function, f of x comma y. That's the standard form. Okay? After we write it as a standard form, what special property can you observe here that causes the problem? Correct. Not continuous. That's one thing. Second, your initial point at 2 to make the denominator 0. That causes the problem. If your initial value is not at 2, then we won't have such problem. Only at 2 we have such problem because the function itself has problem at this point. Now you can see if the function is a good one at one particular point, and at that point provides us initial value, then we should be fine, right? So the natural logic is like that. Okay? Yeah. Yeah, actually that's the result of the existence theorem. So we will see that. Yeah. All right. Yeah, so not in the domain of the function. Yeah. Domain of this function. Domain. Yeah. All right. Now, existence theorem. Here, let me state that theorem and explain. Yeah. But we cannot prove it. Yeah. Out of our scope. Out of scope. Yeah. So let me write that theorem. Given the initial value problem, the general format, yeah, we define a neighborhood of a point. Here we use a formal terminology. Yeah, textbook uses the range, but range could be confusing. Yeah, because in our math terminology, when we use range, we talk about range of the y value. X value we use domain. Y value we use range. So I try to avoid that confusion. Okay? But neighborhood is a formal name. Neighborhood. Yeah, around this point, there is some small interval. So we call neighborhood. Okay? Yeah. That terminology. So the neighborhood, here I use R as in the textbook. X minus x0 absolute value less than a positive number A. That's the neighborhood of x0. Okay? But this region, yeah, we can call it region R. This region is a rectangular region. Okay? Yeah. X direction, there is an interval. Y direction, another interval. Okay? So you get a rectangular region for R. Yeah. So we consider this as a neighborhood of x0, y0 point. Yeah. The setting, yeah. The setting, then the condition. If f function, f of x and y has the following properties, two properties. We need to check two properties. Yeah. Make sure this function is good enough. The first property, it is continuous at all points in R. This R, this region, rectangular region, f must be continuous in the whole region R. The first condition, okay? Continuous, better than defined. The function is defined. Continuous, you know continuous, right? Continuous function. It must be continuous. Okay? All right. Second, it is bounded in R. This function must be bounded. There is an upper bound. Yeah. It cannot be too large. There is a bound, cover it. Yeah. So a bounded function. Yeah, let me explain the bounded function here. Yeah. There exists a number k such that this function f of x, y, the function value, absolute value, less than or equal to this, the k number. Yeah. You can find that k number. Okay? K must be a number. That means it cannot be infinity. We know infinity is not a number, right? K must be a concrete number. So it's not infinity. Yeah. All right. That's the second condition, bounded, the function, f function. Yeah. Yeah, for all x, y in R. Yeah. Then conclusion. Then this initial value problem has at least one solution. That's existence. At least one, could be more, at least one solution in a smaller subinterval of subinterval. It may not be the whole interval. Okay? Could be smaller. Yeah. Sometimes we need to make it a smaller subinterval of the original neighborhood. All right? Yeah. Specifically, how large is the subinterval? Yeah, we need to get some sense, get some idea. How large is the subinterval? The subinterval, we use alpha to tell us how large it is. The alpha value, the minimum of a, comma, b over k. Yeah. Less than or equal to a, smaller than a. Yeah, but we also need to consider b and k value. B over k. That's the existence theorem. Okay? That's the whole theorem. Now, not very hard to understand the conditions, right? We can apply. Yeah. So we only need to understand and apply this theorem. Yeah. The proof out of scope. Yeah. The proof, not easy. Yeah. And if we are math major, then we are required to do the proof. If we are engineer major, we do not need to do the proof. Okay? Theoretical proof. Yeah. So skip it. Yeah. Otherwise, because it's also hard for me. Yeah. The proof. Yeah. Yeah. All right. Now let's do the checking in the previous example, so you can easily see our previous. That's the f of x, y function. Check the first condition. Is it continuous in the region R? No, not continuous, right? Because at this point, it is even not defined. At that point, not defined. Yeah. But someone can argue, I just define it. I define at this point, I assign value 0, for example. But if you define it, then it won't be continuous, right? Yeah, you can easily see. Because people can define at that point. Yeah. But if you define any number, it won't be continuous. You will see, you will prove, no, won't be continuous. Okay? So the first condition is not satisfied. How about second condition? Do you think the second condition, bounded condition, could be satisfied? Bounded condition could be satisfied for some capital K. Think about where x is very close to 2, how large it is. Okay? Let's take y equals 1. Okay? X very close to 2. Yeah. Not equal to 2, but very close to 2.00001. Things like that. Yeah. There, after division, the number could be very large, right? You can make it larger than any given number, larger than k. You couldn't find a k. So the second condition, not satisfied. Yeah. Yeah. So you can easily see, for this example, yeah, the existence theorem does not hold, yeah, and yeah, we know no solution. Yeah. All right. It violates both conditions. Yeah. All right, so we finished existence theorem. Next, B.3, we want to look at uniqueness theorem for first order. Another part, because after we apply existing theorem, we know that IVP problem has at least one solution, greater or equal to 1, but could be more, right? Now, so we have the other half of the theorem, uniqueness theorem, only one. Yeah. You cannot have two, yeah. Only one. Yeah. So also important, uniqueness. Yeah. All right. Uniqueness, so we keep the first part, the same as the previous theorem, okay? The setting part, yeah, the same as the previous one. Yeah. So we just keep it. Yeah. Let's look at a condition. This time, uniqueness, we need more condition, okay? On top of, we still need the previous two conditions. We copy, previous two conditions here, but we need to add two more conditions to get a uniqueness. Yeah. All right. It is continuous at all points R. That's the previous condition, right? Yeah. No? So we keep it. All right. Its partial derivative. This time we need to look at its partial derivative. Okay? Partial y, partial f over partial y, is continuous at all points R. Okay? Yeah. Similar to the first condition, but we change f to partial f over partial y. Second condition. Okay? Yeah. Then, third condition, both f and f sub y, partial y, f partial y, are bounded in R. F, that's the previous, but we add a new one. This function must be also bounded in R. Okay? Yeah. Then we have that uniqueness property. Yeah. So that is, yeah, so that, yeah, these, two inequalities, K and M here. Yeah. Conclusion, then this initial value problem has at the most one solution. The previous one at least, here at the most, okay? Previous one greater or equal to 1, this one at the most less than or equal to 1, okay? Both true, exact 1. Yeah. Exact 1, all right? At the most 1. Furthermore, this initial value problem has exactly one solution. Yeah, because the condition already covered the existence case, right? Yeah, already covered. Yeah. So we should have both existence and uniqueness. So that's why it has exactly one solution. Okay? Yeah. That's the existence and the uniqueness theorem. Yeah. Yeah. So we skip the proof. Yeah. It's not required for us. Yeah. But there is a small paragraph explaining the meaning in the textbook. Okay? There is a half-page explanation. So if you want to understand a little better, so you can read that half paragraph in section 1.7. Okay? Chapter 1, 1.7. That whole section for this topic. Next, we need to move to second order case. After we finish the first order, then second order. Second order, quite different. The situation quite different. Yeah. The property is quite different. Yeah. All right. Yeah, but let's do one example. Yeah. Before we move to second order, let's do one simple example here. Okay, all right. Study the initial value problem, y prime. Here, you can argue this is not a linear, right? Yeah, this is not a linear ODE. Yeah, because y squared, based on our, checking the three conditions, it's not a linear. Yeah. It's not a linear. Yeah. Yeah. Anyway, oh, not necessarily linear, right? Yeah. If you go back to our here, if you go back to our let me write. Yeah, I can write here. If you go back to our previous IVP problem, we wrote like this: general form y prime equals f of x y. We do not say linear, right? We didn't say linear. F function. We only say f function satisfies continuous condition in the region, not necessarily linear, right? Yeah. So here you can see, even if it is not a linear, that theorem holds, still hold. Yeah. So don't worry, you can apply. So here we can apply the existence and the uniqueness theorem. Yeah. Yeah. All right. But this equation is so simple, we can solve it first, right? We can solve it. Let's solve it. We can see the real solution. Then we check with the theorem. Yeah. Solve the equation first. Separable type. Yeah. So we write in this way, then we take integral. Right hand side easy. What's the integral of the left hand side? Some special formula? Anyone? Correct. Yeah. Inverse tangent or arctangent, right? Arctangent. Yeah. So I found another short expression for arctangent. Yeah. A tan. Yeah. I saw somewhere, not to write arc, A-R-C. Yeah. Too long. Yeah. Yeah. A tan. Yeah. Because if you write this way, the inverse that may cause confusion, right? You know, the corner inverse. I'm afraid some students treat it as a reciprocal. If you treat it as a reciprocal, then it's wrong, completely wrong. So I tried to avoid that. Yeah. So let's use A tan, arctangent. Yeah. I see, it's good. Yeah. So let's use it. Yeah. A tan of y equals x plus constant c. Yeah. Then we can take tangent both sides. Y equals tangent of x plus c. Then we can determine that c value from initial condition. So plug in the number, x equals 0, so tan c equals 0. Yeah. What is that c? What is that c? Tangent. Sine over cosine. At which point it's 0, 0. Yes, 0. How about pi? At a pi, is it 0 at pi? Yeah, yeah. You need to be familiar with properties of trigonometric functions. Okay, sine, cosine, tangent, cotangent. Yeah, secant, cosecant. You know, we can get from sine, cosine. Yeah, reciprocal. Yeah. All right. C equals 0, but the question is, it's possible C could be pi. Do we need to worry about that? C could be pi. Should we worry about there is a possibility C equals pi? Yeah. Although, yeah, by logic, yeah, we need to include C equals pi or multiple of pi, any integer multiple of pi. Yeah. But there is a property for tangent function, periodic function, right? Tangent function is a periodic function. What is the period of the tangent function? Period. Oh. Yeah. So you tell me the interval, one interval. Yeah, I know your meaning. From negative pi over 2, what is the length of this interval? Pi. That's the period. The length of this interval is the period. Yeah. So we say tangent function is pi periodic. Pi is the period. That means if you add pi, that period can be dropped, right? Because it's a period, we get back to the same value, right? You add pi as if you do not add anything, right? When you add pi or any multiple of pi, you can drop that pi. You can drop that multiple of pi because the period, by the period thing, the property. So that's why we only need to consider 0, because when you add a pi or multiple, take it away. So we only have this 0 case. Yeah. So we write the solution y equals tangent of x. Yeah. All right. Now let's apply the theorem. Yeah. I mean, right. So that's the, yeah. So there is a name for it. Yeah. This interval. Yeah. Yeah. I forgot its name. Yeah. Define the rectangle R here. Yeah. So here, actually, we can use some positive number a and b to define the rectangle. Okay? Yeah. Here I do not assign any number a, b. I hold a little bit, yeah, because I can change the value as I want. Okay? So here I do not make it certain. Yeah. Our textbook, this example, it is certain. A value, b value given in our textbook. Yeah. All right. So with a, b to be determined, yeah, because I want to squeeze some juice out of it. Okay? Yeah. I want to, do a little more than our textbook. Okay? All right. In the textbook, a equals 5, b equals 3. Okay? Then we apply existence uniqueness theorem and see what happens. Yeah. All right. So let's check the bound of the function. The bound. 1 plus b squared equals k. Yeah. If you use 3, that k equals 10. Okay? Here, I hold the value of b a little bit. Yeah. Because then I have freedom to choose its value to my advantage. Okay? I want to do better than the textbook. Yeah. So here I show you some little technique. Yeah. All right. Existence theorem. Let's look at existence. Yeah. Alpha, yeah, because we need to calculate the alpha existence. It is guaranteed in this alpha subinterval existence. Outside alpha, it's not guaranteed. Okay? Something could happen, we don't know. Yeah, the proof, yeah, because in the proof, the technique of the proof tells us we need to shrink the consideration in the smaller subinterval. Okay? Yeah. All right. But here, since alpha has this expression, we want to make alpha as large as possible. Right? Make alpha as large as possible. Yeah. Then, our result would be better, right? Yeah. So that's something I like to do. All right. Let's look at this b over k expression. B over k. All right. K equals 1 plus b squared. B over k equals 1 plus b squared. B, you just choose any positive number b. You get this fraction. Can you see something we can do here? After we choose some appropriate b, we can make this fraction has the largest value. Can you do that? Yeah. We can change b. All right? Higher, smaller. At a certain point, you get the largest value. If you go higher, it becomes smaller. If you go lower, it becomes smaller. Only at that particular point, it is the largest. Can you see that? Yeah. Here, I want to tell you how to find that point. It's a maximum. Yeah. In your calculus, you need to solve many maximum problem, right? Extrema, maximum, minimum. Yeah. Here, how to find the maximum of this function? Yeah. That's just like a calculus question. You need to find the maximum of this function, right? Yeah. Let's find the maximum. Yeah. Here, I do not take derivative. In your calculus, you need to take derivative. Find the critical point. Then plug in the critical point maximum. Here, I do not use that way. Okay, I use a different way. Can we do division by b, both numerator, denominator? When we do that, numerator 1, denominator b plus 1 over b. To get a maximum of this fraction, can we just get a minimum of the denominator? Because the smaller the denominator, the fraction is larger. 1 over a small number is larger, right? So our question becomes, we want to find the minimum value of b plus 1 over b. Yeah. Can you see better? b plus 1 over b. Are you familiar with this structure? It's a special structure. b plus 1 over b. Because the product of these two terms equals 1. Is that special? b times 1 over b equals 1. The product of the two numbers is constant 1. That's a nice property. Yeah. All right. So here, we want to make this denominator as small as possible, the minimum of this denominator function. Yeah. Here, let me introduce this mean inequality. Have you heard of that? Mean inequality? Mean inequality? Yeah. Yeah. All right. Yeah. Pretty simple. If I write it out, probably you can recognize it. Mean inequality. All right. A plus b over 2 greater or equal to root of a times b. Have you seen this before? Anyone seen? No? No? All right. Think about when you make a fence at your backyard. Okay, make a fence. Okay, the total length of your fence is fixed. The total length, yeah, because you can only buy that much material. The total length, yeah, and your fence should be in a rectangular region. Okay, yeah, rectangular region. Yeah. All right, but you can remember the total length is fixed. You can make different rectangle shapes, right? Yeah. The question, with the fixed total length of your fence, what is the largest area? Can you get the largest area? If you make too skinny, not very large. Okay? Yeah. What is the largest area, in the rectangular area? Thought about that? Largest square shape. Usually fence, there is one side is your house, right? Wall. Yeah, you can use that. Yeah, but here, because if you do that, the answer would be different. It won't be square. Okay, but now we do not consider that wall. Okay, we just all four sides should be included, by the fence. Yeah. Answer is square shape. Square shape. So you enclose the largest possible area. Okay? All right. That result, we can use this to explain. Yeah. A, the width. B, the height. Okay? A could be smaller, B could height. Yeah. But A plus B, the perimeter is fixed. Yeah. A plus B is fixed. Okay? A plus B is fixed. All right. Yeah. Area A times B is the area, right? Area, okay? Yeah. All right. Where the maximum, the equality occurs where A equals B. A equals B, this side is A, that side also A, equality, okay? When A equals B, it's a square. A equals B is a square, right? Yeah. A equals B is a square, all right? Yeah. A equals B, yeah. Or let's look at it in this way, all right? Because we look at the area, right? Area is A times B. We want to make A times B as large as possible, right? Yeah. But based on this inequality, root of the area, is the root of area less than equal to a fixed number, A plus B fixed number, right? Yeah. The perimeter of the fence is fixed. That's assumption. Perimeter of fence fixed. So this A plus B over 2 is a fixed number, all right? But root of your A times B is less than or equal to the fixed number. What is the largest area? Where it equals the upper bound, right? Can we treat this fixed number as the upper bound of root of area? Upper bound, right? Upper bound. When A equals B, you get your upper bound. That's the largest area, right? Because your area becomes the upper bound. That's the largest possible you can get. Okay? All right. So here, this is called the mean inequality. Very basic, yeah, very important. Very important. Yeah. All right. This mean inequality has another representation like this. AM greater or equal to GM. What is AM? Arithmetic mean. Heard of that? Mean. Yeah. Mean. What's the mean? The definition of mean, you have many different definitions of mean, right? What's the mean? Yeah.
Tendency to the center.
Center. Don't confuse with the median. You may confuse.
It's a central value.
Yeah. Central value. Yeah. Yeah. In general, you're right. In general, central value. But what's the specific meaning of central? Then there are many different ways to define. Yeah. When you define central, can we have many different special ways? Yeah. Here, one way, arithmetic mean. Yeah. You add all arithmetic mean of A and B. You add up these two numbers divided by 2. That's a way to define central, right? Midpoint. Yeah. Can you define based on the area? We define the central. We want to look at from the area point of view, central. Okay? So it's another way to define. So we call it geometric mean. Because when you look at the area, it's a geometric property, right? Geometric property. So you take square root. So from the geometric point of view, this is a mean. Geometric mean. Okay? Yeah. And you have other means. Yeah. Harmonic mean. There is another mean. And many other different means. Yeah. But here we only look at these two means. Arithmetic mean always greater or equal to geometric mean. That's the inequality. Very famous. Very famous. Yeah. You need to know that. Yeah. Yeah. Because later when you need to solve the fence problem, you know the answer. Yeah. All right? All right. Now, it tells us equality occurs when B equals 1 over B equals 1. That's the minimum of the denominator, maximum of the whole fraction. Plug in 1. Okay? So we choose B equals 1, so we get this 1/2. Yeah. 1/2. But if we choose 3, as in the textbook, choose 3, B3, we get 0.3, less than 1/2, right? 0.5. So this way we do better than the textbook number. Yeah? All right. Yeah. So then, our subinterval becomes absolute value of x less than 1/2. Our substitute existence subinterval becomes this. Yeah. All right. Then uniqueness, then we do not need to do anything. We just check the bound of its partial derivative. 2b, we know the 2b is a certain number. It cannot be infinity. It's a bound. 2b, if we use 1, 2b just the 2. Yeah. So in the region, its partial derivative bounded by 2. So then, by uniqueness theorem, this solution is unique. Is unique. Okay? Yeah. All right. Yeah. Yeah. Oh, yeah. So we have 5 minutes, but this B.4 is very short. Yeah. Probably we can finish in 5 minutes. Only one slide. Only one slide. We can finish it. So then we take a break. Yeah. For second order, uniqueness, existing uniqueness version, even simpler than the, even simpler than the first order. So we just, finish it before the break. Existence and uniqueness theorem. Yeah. We consider this time homogeneous. Yeah. Only consider homogeneous. Second order, linear ODE with P function, Q function. Yeah. Our, saw this before. Yeah. All right. Then, and also two initial conditions. Yeah. All right. Then, let's look at the theorem. Yeah. Theorem, not very long. Yeah. If P of x and Q of x are continuous functions on some open interval of I, here we only need to know some open interval. We do not even try to measure how large it is. Okay? Just some open interval of I. Okay? Yeah. Then the above initial value problem has a unique solution y of x on I. The uniqueness part. Yeah. That's simple. Continuous. Yeah. That's simple. Yeah. The proof is not simple. Yeah. The theorem, statement, simple. All right. All right. Then, PQ continuous on open interval I, another half, that has a general solution. Yeah. Because uniqueness, next we want to, so here, just a minute. Yeah. When you see has a unique solution, already include existence and uniqueness, right? Existence, you have one, existence, right? Unique, only one. Already both, yeah? So this short statement already covers both existence and uniqueness. Yeah, so simple, yeah, the statement. Yeah. All right. This, we want to get more properties. Yeah, more properties. All right. Continuous, yeah, same condition as before. This time we say it has a general solution y on I. It has a general solution. Yeah. And every solution, here we use capital Y of x, every solution can be represented as the linear combination of two special solutions, y1, y2, and where y1, y2 is any basis of the solutions. That's, more properties. Yeah. Yeah. You can treat it as another theorem. Yeah. So we get more information. The information is any solution, every solution can be represented as a linear combination of, two functions inside the basis. basis. Yeah. This means there is no singular solution. Do you know? I mentioned that singular solution before. Do you still remember what's the singular solution? A little bit? Singular. Yeah. Let me remind you. Yeah, from the name you can guess a little bit, right? Singular. Something very special, not normal, right? Yeah, quite special, singular, all right? Singular solution here, solutions not obtainable from a general solution. You cannot choose special C1, C2 to get that singular solution. Not obtainable from the general solution expression, okay? That's the singular solution. Yeah. Remember, when we did that example, population, remember that population, that equation? What's the name of that equation? Population? AY minus BY squared, remember that one? There is a singular solution, y equals 0. It cannot be represented by the general solution. So it's a singular solution. Yeah. This tells us second order homogeneous ODE, there is no singular solution. How about that? Yeah. How good it is. No singular solution. Okay? Yeah. But for this special case, second order homogeneous, yeah. Right? It's good. Yeah. All right. Break time. Yeah. After 10 minutes, we do our little problem solving session number 1.